So, we have seen several techniques for SOC testing, and there are various problems like designing the wrapper itself, and then designing the TAM part, and then doing the scheduling. And if we try to exploit different features of the ATE, the test equipment, then again there are variations in terms of the operations, the schedule, the architecture that we can get, then the operational flexibility that we can get, and accordingly we can use different techniques that we have seen that we have seen for the SOC testing. So, to conclude this SOC testing part, so we can say that test reuse, test time minimization and test compression are necessary to reduce test cost for SOC. So, this is one very important issue. Test reuse, that same test if we can use for multiple cores, okay, then this may be done. There are some works that talk in that direction, combining test patterns for different cores and then sending those test patterns. Okay. So, that way the test time can be minimized. Then the compression. So, compression will be useful because this tester memory requirement will become low, and this transfer time from patterns from tester to the chip. So, that will also get reduced. So, that way we can have this thing, this compression is also going to help us in reducing the test time. Then there are wrapper or TAM optimization and test scheduling. So, this can reduce test time for the SOCs. So, wrapper optimization, we have seen that giving different widths to the wrapper, so of chains of this course. So, they can have different types of test times, the test time may get reduced, and this TAM optimization has to be done because this TAM we can do a partition TAM. So, we can may not go for partitioning. So, we can go for different type of scheduling policies. We can go for different TAM architectures like say virtual TAM, like then this high speed TAM, multiple multi-rate TAM. So, like that we can go for various types of TAM architectures that can exploit the features of the ATE. So, in virtual TAM it offers advantages because on chip TAM wires are not limited by the number of available pins of the SE on the SOC. So, this we can the on chip from the ATE we have got a number of pins coming. So, the structure was like this. If this is the ATE, from this ATE, say suppose say n number of lines are coming, then when it is reaching the SOC, so the SOC has got n number of pins here, but here I have got that expander, that serial to parallel converter. So, the n line coming here is expanded into a number of lines here. So, that is actually used for testing the cores that are there in the system, and then all of them are again combined into n. So, this is combined into n and it is going back to the ATE. So, this if this here the number of lines is m. So, we have seen that this virtual TAM structure can make m to be larger than n. So, from the SOC pin side, so SOC pin remains at n, ATE channel remains at n, but inside the for scheduling, so we see that it is increased to m. So, that way this test scheduling can be benefited. So, it results in better utilization of high speed ATE channels. It reduces that's how it reduces the testing time. And with this port scalable ATE channels, so they can be made to operate the ATE channels can be made to operate at different frequencies. So, if embedded cores are of different frequency, the maximum frequency at which their testing can be done are different, then we can try to exploit those information, and then we can try to design the TAM so that these ATE channels are utilized. So, high speed ATE channels can be utilized for applying test patterns faster to the chip. So, after looking into this SOC testing techniques and all that, so next we will look into another topic which is known as network on chip. So, what is network on chip? So, it is so in SOC what we have done is that the basic philosophy behind designing SOC was that if I have a board, and in this board if I have got these individual chips, then the problem was that this off chip communication was problematic. So, off chip communication was much slower than the on chip communication. Now, when this is translated into SOC design, so what is happening is that we have got a silicon wafer, and onto this silicon wafer all these components are fabricated. So, all these chips, so this is say C1, C2 and C3. Now, I get the corresponding IPs from the vendors. So, this IP1, IP2 and IP3. So, they are fabricated on this silicon float, and then the connection between them. So, they are also onto this, like here I have got connection from C1 to C3, here IP1 to IP3 I have got a connection. There may be another connection from IP2 to IP3, where there was a board level connection from C2 to C3. So, the advantage that we get is this off chip communication that we had from C1 to C3 or C2 to C3, they are getting translated into on chip communication. So, they are going at a same rate as the original one. So, the rate at which these individual IP cores can operate, these channels can also transfer data. So, these signal lines, they can transfer data at the same rate. So, the delay is much reduced compared to the off chip connection. However, there are problems in the sense that you see there will be large number of lines that are running in the system, because if say IP1 is a CPU and IP2 is a memory, then what is required? From CPU the address bus will come, the data bus will come and the control bus will come. Now, this address bus, data bus, so for modern processors, so they are very wide. As a result, you see there will be large number of lines that needs to run parallelly through between this CPU and memory. So, this line that I have drawn from IP1 to IP2, if IP1 is CPU and IP2 is a memory, then the width of this line is significant. So, this is the sum of the width of this address, data and control lines. So, that way it is going to be large number of lines that we need. Now, in this case, when there are a large number of lines running parallelly, so I have got large number of lines running parallelly. Now, we have got the problem of crosstalk, we have got the problem of interference between the lines, and that way on the board level we had this problem, but it was not that much of an issue, because this connection. So, the system was operating at a much lower frequency. So, the delay of these channels, so they were these external channels, so they were deciding the delay of this communication, the delay of this the frequency of this entire board. And when we convert it into SOC, the basic idea was to have a better speed performance. So, I want to increase the frequency to say gigahertz range. Now, the IPs, the individual IPs that are designed, so they are designed very efficiently, and suppose they can operate at the gigahertz range, but the communication part, so they cannot operate at gigahertz range due to these problems. Okay. So, there is large number of lines running parallelly, so we cannot have this type of situation. So, what is required? So, as a solution, so there can be the standard solution is to have a bus, and from this bus all these IPs will be hanging. So, this is IP1, this is IP2, this is IP3. So, all of them are hanging from this bus, and there must be a bus master will be there, and whenever any IP wants to communicate with another IP, so it will tell the bus master that I want to use the bus. So, say that way, so thus bus master will generate a grant, and these two IPs will do the communication between them through this bus. Advantage, we definitely save on the number of these lines that are running throughout the chip, because all these lines will be replaced, because now everything will be happening over this bus, and this IPs, they need to communicate some sort of coded message through this bus for this address, data and control. Say IP1 is CPU and IP2 is memory, so they will do this thing. So, that makes the process regular, and we can have multiple levels of buses and all that, but at the same time this bus based communication, it has got limitation. So, you cannot go on hanging devices from the bus. Okay. So, that will increase the capacitance of the bus, and that will also the resistance of the bus. So, delay of the bus will become unacceptable after we have connected a few devices to the system. So, on the other hand, we want the maximum parallel communication. So, another problem with bus is that at one point of time only one communication can go through the bus. So, there is a communication bottleneck. So, I cannot have more than one communication going on simultaneously on a bus. So, if I have got hierarchical bus, then to some extent we can have this parallelism, but still if there is a communication across these buses, then one such communication will stall all other communications. So, that way we have got this we have got problems with this bus based communication mechanisms. So, what we want is something like a point to point sort of communication, where every module can communicate with every other module directly, but that will require large number of signal lines running through the system, running through the chip. So, we need some solution, to this problem, and this network on chip is a solution that has been proposed for designed for solving this communication problem in the SOC. So, it is otherwise a system on chip design. However, the communication procedure between the between the cores, they follow a particular paradigm. So, we will see how this can be done. So, for future SOCs with large number of cores and increased interconnect delay, traditional point to point or bus based communication architecture becomes new bottleneck. So, bus has, I have said that the bus has got it cannot do parallel communication, more than one communication cannot be done simultaneously, and point to point means there are large number of lines running through the chip. So, both of them are problematic, and compared to a board, a chip has got much lesser area, and this with the increasing device density, more amount of logic will be put into the system. So, there will be more amount of communication between these modules that we put on the chip. So, that way we can have this communication architecture that becomes a bottleneck. So, that has to be resolved. So, traditional communication architectures cannot meet system requirements of bandwidth, latency and power consumption. So, bandwidth, you cannot transfer at a very high data rate. Latency, so one communication will take more time because of the delay that is incurred in the bus, and power consumption. So, if you have got point to point communication, the power consumption will be very high. Similarly, bus also the power consumption is very high, and there are several techniques, bus encoding strategies that has been proposed, but incorporating them will require extra hardware, and that will add complexity to the system. So, we have got these problems with the traditional communication systems that do not meet the requirements of bandwidth, latency and power consumption. So, integrated switching network, it has been proposed as an alternative approach to interconnect cores in SOC. So, what it says is there will be a network in the system, in the chip itself, and these components that need to communicate between themselves, they will do that using that underground the basic network that is available on the chip. So, this is the idea is that similar to this say computer network. So, we have got large number of computers to be connected. So, one possibility is that we can put all those computers on a bus and drop them from a bus based communication, but the difficulty is that, so creating such a bus is a problem. So, in a distributed processing environment, what we do, we create a backbone network, and from that backbone these individual computers may be dropping, or it may be each backbone may be feeding a sub network, and from the sub network we have got the connection to the individual computers. So, similar such situation can be done like just like distributed computing. So, this backbone design is such that they can do communication between this within the backbone very easily and at a very high data rate, and then the rest of the communications are taking place. The same thing is duplicated here in a just like in a distributed processing environment. So, here also it is duplicated like that. So, this there will be an interconnect integrated switching network that is incorporated into the chip, and these networks, they rely on a scalable and reusable communication platform which is known as network on chip or NOC system to meet two major requirements, reusability and scalable bandwidth. So, reusability means the same channel can be used for doing communication between a number of such IP cores. So, at the definitely not at the same time, but over the time. So, they can be used for doing this communication, and the bandwidth. So, as you are adding more and more IP cores, then this bandwidth utilization will improve till a saturation point is reached. After that, if you increase that network size, again the bandwidth utilization will start increasing. So, this is the typical structure. So, we have got this routers and the interconnection between them. So, they actually form the backbone network. So, in this particular diagram we have got 6 routers and they are connected in a mesh fashion. Okay. So, there is a 2-dimensional mesh fashion into which they are connected, and from this individual routers, so the cores are connected. So, this is a 2D mesh, this is basically a 2 by 3 mesh. Now, we can have a mesh of more dimension, like you can say that okay, I will have a 4 cross 4 mesh where the situation is like this. So, this is a 4 cross 4 mesh, and at each of these corners we have got one router. So, we have got the routers at these points. Now, from a router there are 4 channels that are going out in general. So, there are one going to the left neighbor, one to the right neighbor, one to the top and one to the bottom. Say this is a router, so it has got 4 neighbors like that. So, these channels they are called global channels, and these channels are parallel channels. Now, I can, if I want to connect some IP core to the system, so I can do it, I can connect it to the router. Like with this router I can have some core IP1 connected here. So, maybe my CPU is connected here, the IP which corresponds to the CPU is connected here, and the IP for the memory is connected there. So, this is the memory. Now, this CPU, when it wants to get some data from memory, so what will it do? It will not send this address data control lines to the memory as some signal lines, rather it will prepare a message. Okay. In that message, it will tell it will put the memory location address from where it needs to get the data, and it will send that message over this network. So, there has to be some routing policy. So, these individual routers they will follow some routing policy. A very simple routing policy may be the XY routing. So, that any message that is to be transmitted is transferred in the x direction first and then in the y direction. So, it will go like this, then it will come down like this, and it will finally reach this memory. So, on getting this memory, so on getting this message, this memory will prepare a return message, and is in the return message it will have the content of the location, and then it will send it to this CPU, and now maybe it will go like this in the XY routing fashion. So, first in the x direction and then in the y direction. So, this way this course may be communicating. So, you see that total electrical signal exchange between the IP cores, it is modified to message exchange between them, and this communication is taking place via this interconnection network that we have and the routers and the links. Okay. Now, the mesh is just an example. So, you can have many other topologies, like you can have a ring topology, you can have a star topology, torus topology, then there are tree topologies, butterfly fat tree topologies. There are many such topologies that have been proposed, but mesh is the most popular one because this is a very regular one, and this design is very simple, and it has got many other features that you can find out if you are interested. You can look into some distributed processing literature, and there you can find the benefits of having mesh. So, why mesh is so popular, but what has happened is mesh has become the most popular architecture. So, every router, if you see in more detail, so if this is a router, so this router has got a number of ports. So, this is called, this is the top port, this is the bottom port, this is the bottom, then we have got left and right. So, they are going to the 4 neighbors of the process of the router. So, this is the router R, and there is a local port with the router. So, this is the local port of the router to which the core will be connected. Okay. So, it is not mandatory that all routers will have cores associated with them. So, that is again another problem of this network on chip design, like how can we decide which cores be assigned to which router, but we will not go into that. So, basically say finally, when the designer has finished, so designer has done it like this, that these cores are attached to different routers. Okay. So, cores are connected to NOC by routers or switches, and data are organized by packets and transported through the interconnection network. So, message that has been formulated, so it is divided into packets, and the packets will traverse through this network to reach the destination. Various network topologies and routing algorithms can be used to meet requirements of performance, hardware overhead and power consumption. So, there are various topologies that have been proposed, and then again there are innumerable number of routing algorithms that have been proposed. So, XY is just one of them. Then you can have some table driven routing, some fault tolerant routing. So, there are many such policies that have been proposed in the literature. So, what is the difference, like when we are coming to the testing point, then what is the special feature that this NOC testing has? So, the greatest difference between NOC testing and SOC testing is on test access mechanism design. So, you see, in case of SOC, the SOC testing, the problem was that to send the test pattern to a particular core, I had to, one possibility was that I can use the functional path passing through different cores, and then the associated difficulty that we had is we do not know the details of the individual cores. So, we cannot find out the excitation sequence by which the particular pattern can be sent through that core. Okay. So, in case of NOC, what has happened is, so that problem is a bit resolved. So, in SOC we solved that problem by having a dedicated test bus or test architecture embedded into it, and then from this input port we are from the ATE we are feeding the test patterns to the test architecture, and the responses are obtained. So, that way it was solved by having some additional test architecture embedded into the SOC. On the other hand, this one NOC, we can utilize the on chip network itself. So, there already a network is existing through which I can possibly reach any of the cores without going into other one. So, by traversing through this router network, I can reach any of the cores in the system. So, this on chip network of the NOC can be reused as a TAM for test packet delivery, and theoretically no TAM interconnects are required to be invested. So, this is, of course, you can say that okay, it will go through the router network. So, that way it will require some time to go compared to our test bus architecture where it will be direct, but so TAM architecture where it will be direct, but that is an overhead. Okay. So, if we are happy with the underlying this router network, then we can use it for transferring the test patterns through the router network. So, test time can be reduced by network reuse even under power constraints when minimized pin count and area overhead. So, test time can be reduced because if the ATE can supply test data parallelly to over two different channels, then we can feed that test data to different cores, and they can be tested in parallel. So, that way we can do a parallel testing of this cores. That way it can reduce this testing time. Power constraints, so individual cores, their power values are there. So, we can follow that, we can restrict ourselves within that power constraint. Pin count is minimized because what is required is that we can transfer it to any of the router, and from there it can be sent to the desired core to which we want to test. And generally more cores can be tested in parallel than TAM based SOC testing. So, TAM based SOC, the problem was that we cannot test to more than one core per TAM, and if there is if the TAM lines for a partition TAM arrangement. So, if more than one TAM cannot be tested simultaneously on a TAM line, and if it is a flexible TAM architecture, then for a core to be tested, all the TAM lines required by this particular core must be free. So, this type of limitations were there. So, what we can do, we can in case of NOC based architecture. So, we can test more number of cores, because now none of them are on TAM. So, it does just depends on the availability of NOC channels and the availability of this core, the router path through the to the core for doing the test operation.